In this chapter, we will firstly understand some of the properties of gases, and then see as to which rules or which physical rules apply to this state of matter. Previously, we did mention that there were three states of matter: solid, liquids, and gases. The reason we're picking up gases during our study is because gases are the easiest to understand because of the way they react against different physical attributes. Just a little revision of what gas particles were. If you recall, gas were composed of small particles, and these particles were far apart. So if I was to draw a section and I was to represent gas particles would be far away from each other. The particles of the kinetic theory of gases states that gas particles would move in a straight directions. Now I want you to think about it. Do you think this would work or not? These are the postulates that we are reading about the kinetic theory of gases, and at the end I will ask you to tell me which ones seems to be incorrect. So that's the first one we did. The second one is that there is no attractive or repulsive forces. That means these particles are independent of each other, so each particle would be going in its own straight line. Okay. The third thing is the particles are very far apart, and which I did draw it over here so you can see that the particles are much farther apart compared to the solids and liquids, where the particles will be closer to each other and having more attractive forces. They have very small volume compared to the volume of the container that's kept. So here's an image which shows that this is the volume of the container, and the particles are far apart, and they actually occupy very limited volume as compared to the entire volume of the container. And lastly, the kinetic energy increases with increased temperature, which states that if I was to put a flame underneath this container and increase heat over here, then the particles would start moving faster or closer. Now, if you look at all of these postulates of the kinetic theory, you can pretty much see that there's one that doesn't really make sense, and that is this one. Gas particles do not move in a straight line. They will collide with each other. With collision, it will result in a path in which, if this was a particle and there was another particle over here, each particle would go straight, and maybe this particle would go here, it would collide and then go in this direction and in this direction. So there would be a random movement of particles in a fashion of a zigzag pattern. So based on the kinetic theory of gases, the first statement is not true. However, the other statements are pretty much true. We live in a sea of gases. So if you consider the Earth, and the Earth is surrounded by, if I was to draw Earth over here, I'm not very good at drawing. So if this was the Earth, then it is surrounded by gas particles, and we are, as a matter of living, at the bottom of this sea. So because we have gas particles all around us, and as we go above, or as we go higher up, the air gets thinner, is because there's less gas on the top. Okay, so this was mainly introduction to the gases. Hang on, I'm just having a little difficulty in moving to the next slide. I'm going to go this way. I guess I'd have to clear ink, go to the next. Okay, there it is. Sorry about that. It was I'm sort of new with this setup right now. All right, now coming back to the properties of gases. Gases, there are certain attributes that can be given to gas, and these will affect the behavior or the role of the gas. So the four attributes that we will look at, or the four properties that we're studying, are pressure, that's the first one, then volume, the symbol as you can see is V, temperature, that's T, and the amount of gas, which is N, and which we just did in the previous chapter. So keeping these in mind, let's just describe each one of them. The pressure is defined as all the particles of the gas forcing itself on the wall of the container. So if you were to imagine a balloon, and in the balloon you have the gas particles exerting pressure on the walls of the balloon, and if you were to increase the particle of the boundary of the balloon, then and thus you could do that by increasing more air particles or gas particles in there. So they will exert pressure, and you know what happens to a balloon like that if it gets deflated over time. There's less pressure to it. Same thing you can imagine on a tire or a bicycle tube. The pressure is always, in physics, pressure is defined as a force per unit area. So that is the particles exerting force, which is later in physics defined as weight of an object, which is later defined as mass times gravity. So pretty much the weight, in layman language, if you can think of the weight per unit area, that would be the pressure. So if you have more weight or larger amount of weight in a smaller amount of area, or per square inch, or per cubic centimeter, then you would have higher pressure. Think of the backpack that you could carry if you were to consider the chemistry books. If I was to place 10 of these books in your backpack and have you carry it, and we have two kinds of backpacks. One is with a broad strap, and one is with a thinner or a finer strap. You know that it will hurt more with the finer strap or the thin one, because the pressure is more cutting into your shoulder with that weight. So that was more about pressure. Let's talk about volume. Volume is always going to be the space that's occupied by the gas. The units for volume are either liters or milliliters. Temperature is the rate of motion of the particles, and temperature is always going to be measured in Kelvin. Though the Celsius can be taken in, but when we do calculations for within this chapter, we will always change our temperature conversions to Kelvin. And the amount of gas is the mass of gas that's present, and either it will be expressed in grams or in moles during our calculations. Coming back to the pressure, there are many units of pressure, and we will only do these three. We'll get rid of torr. We will not mention torr, and as a matter of fact, no, we will mention torr. We will get rid of Pascal. We will not study Pascal, so you can cross this out. We will study atmosphere, millimeters, mercury, and torr. Those are the three units that you will associate with pressure, and we will go into each one of them in a little bit. So here is the same example that I gave you before about the the mathematical calculation of pressure is force per unit area, and the units for these are atmosphere and torr and millimeters mercury. 1 atmosphere is a unit which is equivalent to 760 millimeters mercury, and 1 atmosphere is also equal to 760 torr. So considering this, you can see that torr equals millimeter mercury. So if we were to take any unit, for example, 1 torr would be equal to 1 millimeters mercury. If we have 560 torr, then that would be equal to 560 millimeters mercury. So hoping this is making sense. These two units are equivalent to each other. However, if you have to convert one to the other, you would have to go back and we'll go back over here. This today is okay. So in this particular slide, let's look at the image that's from your book. And you can see in this particular image over here, this shows you a person standing on the surface of the earth, and all the gas particles are almost exerting pressure on the person's head. And this pressure is exerted by the column of air that would be considered right on top of the person. And this is almost the particles of gas particles in the atmosphere creating a pressure. This pressure at sea level is considered to be 1 atmosphere. So at sea level, the pressure is the max that it can hold. That's the maximum pressure at sea level, which is 1 atmosphere. Now, as you can see, if you were to be at a region which is higher up in elevation, which is above sea level, then you can see what happened with the pressure, because now you have less air particles exerting pressure on you. So at higher altitudes, the pressure will be lower. And at higher altitude, now the density of air is also less, because density is mass per unit volume, and there's less mass of the particles over here. Now these two combinations are interesting, because when you listen to the weatherman, they usually will tell you, or they can predict the pattern of the weather based on the atmospheric pressure. Usually when you have rainy days, because there is a cloud coverage, let's just draw a little bit of cloud over here. There was cloud over here. This cloud coverage is almost a barrier, and this barrier, because of this barrier, the particles that are exerted are the particles of the cloud actually will prevent the air pressing on the surface of the earth. So at that time, the pressure is actually less. But when you have a clear day, then you have all the atmosphere or all the gases particles that are above the surface of the earth, and that's giving pressure. So pressure will be high at that time. This is actually talking about the density, lower at higher altitude and higher on a rainy day. And I'm giving you examples of pressure, so there's no contradiction over here. There are two different factors that we're looking at, and that's why it seems like one is the one or the other. Now, what is a barometer? Barometer is a barometer is mainly a gadget, and this gadget is used to measure atmospheric pressure. And the most primitive kind of gadget was designed using a column of mercury. They used column of mercury because mercury is the heaviest liquid that's present as a natural element. Now, this was taken by taking a bowl, which is shown over here, like a shallow bowl, which was filled with liquid mercury, and then a meter-long glass tube, which has an opening on this end, but it has a closed surface over here, was filled with mercury and turned upside down. You can pretty much imagine that by thinking of a glass, and you fill it with water and you turn it upside down. And if you do that on a bowl that also already has a liquid, there can be two scenarios. One scenario would be that the column would start falling and the liquid will actually go outside this container. And the other scenario, I'm going to go ahead and use the different color for that, would be that the pressure outside is forcing the liquid to go up. Now these two will depend, the two scenarios would actually take into effect depending the pressure of the atmosphere. If the pressure outside is greater, if this is greater, then yes, the liquid will go up in pressure and the column, as we call it, will rise. However, if the atmospheric pressure is less, then the column will start falling and the mercury will come down, and this is called as column falling. Now this is what I was talking about in the previous slide with the weather person. So in days when there is clouds outside, the barometric pressure starts falling because there is more pressure inside the column as compared to less. On the other hand, when we have a clear day, the column usually rises. Now, another notice that I want to give out is the units that are used by the weather person. The weatherman usually uses units of pounds per square inches, and we're not really using that because it's not a metric conversion. But notice that whenever there's a rise in the column, that's usually predicted by a clear sunny day, and when the column starts falling, then that is usually predicted as a storm that's coming up. Okay. Now, based on